Have adequate facility and professional teaching staff to support the lecture process. We will always create technology that is oriented toward the benefit of the people, to improve the people's welfare and create the developed society. The Faculty of Engineering, Universitas Muhammadiyah Yogyakarta.
Daerah Istimewa Yogyakarta merupakan sebuah provinsi di Pulau Jawa yang terkenal akan kekayaan budaya dan pariwisatanya. Pelajar dari berbagai penjuru negeri, bahkan internasional, memilih Yogyakarta sebagai tempat menempuh pendidikan. Salah satu perguruan tinggi swasta terbesar di Yogyakarta adalah Universitas Muhammadiyah Yogyakarta. Kampus yang berdiri pada tanggal 1 Maret 1981 ini berlokasi di Jalan Brawijaya, Keblakan, Taman Tirto, Kecamatan Kasihan, Bantul, Daerah Istimewa Yogyakarta. UMY telah mendapatkan akreditasi dengan peringkat A berdasarkan surat keputusan dari Badan Akreditasi Nasional Perguruan Tinggi. UMY juga telah mendapatkan akreditasi tingkat internasional dari QS Stars dengan perolehan bintang 5 untuk bidang fasilitas, bintang 5 untuk bidang pengajaran, dan bintang 5 untuk bidang daya serap lulusan. UMY memiliki 9 fakultas dan lebih dari 30 program studi yang terpadu dalam area seluas 32 hektar. Universitas Muhammadiyah Yogyakarta terus berusaha untuk mencapai tujuannya, yaitu terwujudnya sarjana yang beriman, bertakwa, dan berakhlak mulia, yang mampu mengamalkan dan mengembangkan ilmu pengetahuan dan teknologi, serta berguna bagi umat, bangsa, dan kemanusiaan. Teknik Elektro merupakan salah satu program studi unggulan yang terdapat di Universitas Muhammadiyah Yogyakarta.
Visi kami adalah menjadi program studi teknik elektro yang unggul dalam inovasi bidang sistem tenaga listrik, didukung teknologi cerdas di tingkat nasional dan diakui di tingkat internasional pada tahun 2025 berlandaskan nilai-nilai Islam untuk kemaslahatan umat. Pada saat ini, alhamdulillah atas berkat rahmat Allah Subhanahu wa taala dan didukung usaha keras dari seluruh sivitas akademika Teknik Elektro UMY, kini Prodi Teknik Elektro UMY telah terakreditasi A dari Badan Akreditasi Nasional Perguruan Tinggi. Konsentrasi program studi Teknik Elektro UMY adalah yang pertama yaitu sistem tenaga listrik, yang kedua adalah sistem telekomunikasi, yang ketiga adalah sistem kontrol dan instrumentasi, yang keempat adalah sistem elektronika, dan yang kelima adalah sistem komputer dan informatika. Kemudian kualifikasi dari dosen-dosen teknik elektro UMY, alhamdulillah dosen teknik elektro UMY merupakan lulusan yang qualified, yang berasal dari perguruan tinggi yang ternama baik di dalam negeri maupun yang berasal dari luar negeri, di mana kualifikasi pendidikannya adalah minimal S2 dan mayoritas saat ini telah berpendidikan S3.
Selain sumber daya tenaga pengajar yang berkualitas, Teknik Elektro UMY juga menyediakan berbagai fasilitas yang mampu menunjang pengembangan diri para mahasiswanya, seperti laboratorium. Laboratorium yang terdapat di Teknik Elektro UMY terdiri dari laboratorium telekomunikasi, laboratorium rangkaian listrik, laboratorium digital dan mikroprosesor, laboratorium elektronika, laboratorium instrumentasi dan kendali, serta laboratorium komputasi dan perancangan. Mahasiswa Teknik Elektro UMY juga telah mengukir banyak prestasi baik di tingkat regional, nasional, dan internasional.
Universitas Muhammadiyah Yogyakarta, Young and Global. Welcome to the Faculty of Engineering. We are part of the Muhammadiyah Development Center and play a role in the engineering field. Currently, we are developing technology and global-oriented innovation through developing cooperation to an international level based on Islamic values for the benefit of the people. Through education, we develop students to become excellent and Islamic graduate, and we do research and community service professionally. We are also a medium for students to develop an entrepreneurial spirit. Have adequate facility and professional teaching staff to support the lecture process. We will always create technology that is oriented toward the benefit of the people, to improve the people's welfare and create the developed society. The Faculty of Engineering, Universitas Muhammadiyah Yogyakarta.
Daerah Istimewa Yogyakarta merupakan sebuah provinsi di Pulau Jawa yang terkenal akan kekayaan budaya dan pariwisatanya. Pelajar dari berbagai penjuru negeri, bahkan internasional, memilih Yogyakarta sebagai tempat menempuh pendidikan. Salah satu perguruan tinggi swasta terbesar di Yogyakarta adalah Universitas Muhammadiyah Yogyakarta. Kampus yang berdiri pada tanggal 1 Maret 1981 ini berlokasi di Jalan Brawijaya, Keblakan, Taman Tirto, Kecamatan Kasihan, Bantul, Daerah Istimewa Yogyakarta. UMY telah mendapatkan akreditasi dengan peringkat A berdasarkan surat keputusan dari Badan Akreditasi Nasional Perguruan Tinggi. UMY juga telah mendapatkan akreditasi tingkat internasional dari QS Stars dengan perolehan bintang 5 untuk bidang fasilitas, bintang 5 untuk bidang pengajaran, dan bintang 5 untuk bidang daya serap lulusan. UMY memiliki 9 fakultas dan lebih dari 30 program studi yang terpadu dalam area seluas 32 hektar. Universitas Muhammadiyah Yogyakarta terus berusaha untuk mencapai tujuannya, yaitu terwujudnya sarjana yang beriman, bertakwa, dan berakhlak mulia, yang mampu mengamalkan dan mengembangkan ilmu pengetahuan dan teknologi, serta berguna bagi umat, bangsa, dan kemanusiaan. Teknik Elektro merupakan salah satu program studi unggulan yang terdapat di Universitas Muhammadiyah Yogyakarta.
Visi kami adalah menjadi program studi teknik elektro yang unggul dalam inovasi bidang sistem tenaga listrik, didukung teknologi cerdas di tingkat nasional dan diakui di tingkat internasional pada tahun 2025 berlandaskan nilai-nilai Islam untuk kemaslahatan umat. Pada saat ini, alhamdulillah atas berkat rahmat Allah Subhanahu wa taala dan didukung usaha keras dari seluruh sivitas akademika Teknik Elektro UMY, kini Prodi Teknik Elektro UMY telah terakreditasi A dari Badan Akreditasi Nasional Perguruan Tinggi. Konsentrasi program studi Teknik Elektro UMY adalah yang pertama yaitu sistem tenaga listrik, yang kedua adalah sistem telekomunikasi, yang ketiga adalah sistem kontrol dan instrumentasi, yang keempat adalah sistem elektronika, dan yang kelima adalah sistem komputer dan informatika. Kemudian kualifikasi dari dosen-dosen teknik elektro UMY, alhamdulillah dosen teknik elektro UMY merupakan lulusan yang qualified, yang berasal dari perguruan tinggi yang ternama baik di dalam negeri maupun yang berasal dari luar negeri, di mana kualifikasi pendidikannya adalah minimal S2 dan mayoritas saat ini telah berpendidikan S3.
Selain sumber daya tenaga pengajar yang berkualitas, Teknik Elektro UMY juga menyediakan berbagai fasilitas yang mampu menunjang pengembangan diri para mahasiswanya, seperti laboratorium. Laboratorium yang terdapat di Teknik Elektro UMY terdiri dari laboratorium telekomunikasi, laboratorium rangkaian listrik, laboratorium digital dan mikroprosesor, laboratorium elektronika, laboratorium instrumentasi dan kendali, serta laboratorium komputasi dan perancangan. Mahasiswa Teknik Elektro UMY juga telah mengukir banyak prestasi baik di tingkat regional, nasional, dan internasional.
Universitas Muhammadiyah Yogyakarta, Young and Global. Welcome to the Faculty of Engineering. We are part of the Muhammadiyah Development Center and play a role in the engineering field. Currently, we are developing technology and global-oriented innovation through developing cooperation to an international level based on Islamic values for the benefit of the people. Through education, we develop students to become excellent and Islamic graduates, and we do research and community service professionally. We are also a medium for students to develop an entrepreneurial spirit. Have adequate facility and professional teaching staff to support the lecture process. We will always create technology that is oriented toward the benefit of the people, to improve the people's welfare and create the development desired. The Faculty of Engineering, Universitas Muhammadiyah Yogyakarta.
Daerah Istimewa Yogyakarta merupakan sebuah provinsi di Pulau Jawa yang terkenal akan kekayaan budaya dan pariwisatanya. Pelajar dari berbagai penjuru negeri, bahkan internasional, memilih Yogyakarta sebagai tempat menempuh pendidikan. Salah satu perguruan tinggi swasta terbesar di Yogyakarta adalah Universitas Muhammadiyah Yogyakarta. Kampus yang berdiri pada tanggal 1 Maret 1981 ini berlokasi di Jalan Brawijaya, Keblakan, Taman Tirto, Kecamatan Kasihan, Bantul, Daerah Istimewa Yogyakarta. UMY telah mendapatkan akreditasi dengan peringkat A berdasarkan surat keputusan dari Badan Akreditasi Nasional Perguruan Tinggi. UMY juga telah mendapatkan akreditasi tingkat internasional dari QS Stars dengan perolehan bintang 5 untuk bidang fasilitas, bintang 5 untuk bidang pengajaran, dan bintang 5 untuk bidang daya serap lulusan. UMY memiliki 9 fakultas dan lebih dari 30 program studi yang terpadu dalam area seluas 32 hektar. Universitas Muhammadiyah Yogyakarta terus berusaha untuk mencapai tujuannya, yaitu terwujudnya sarjana yang beriman, bertakwa, dan berakhlak mulia, yang mampu mengamalkan dan mengembangkan ilmu pengetahuan dan teknologi, serta berguna bagi umat, bangsa, dan kemanusiaan. Teknik Elektro merupakan salah satu program studi unggulan yang terdapat di Universitas Muhammadiyah Yogyakarta.
Visi kami adalah menjadi program studi teknik elektro yang unggul dalam inovasi bidang sistem tenaga listrik, didukung teknologi cerdas di tingkat nasional dan diakui di tingkat internasional pada tahun 2025 berlandaskan nilai-nilai Islam untuk kemaslahatan umat. Pada saat ini, alhamdulillah atas berkat rahmat Allah Subhanahu wa taala dan didukung usaha keras dari seluruh sivitas akademika Teknik Elektro UMY, kini Prodi Teknik Elektro UMY telah terakreditasi A dari Badan Akreditasi Nasional Perguruan Tinggi. Konsentrasi program studi Teknik Elektro UMY adalah yang pertama yaitu sistem tenaga listrik, yang kedua adalah sistem telekomunikasi, yang ketiga adalah sistem kontrol dan instrumentasi, yang keempat adalah sistem elektronika, dan yang kelima adalah sistem komputer dan informatika. Kemudian kualifikasi dari dosen teknik elektro UMY, alhamdulillah dosen teknik elektro UMY merupakan lulusan yang qualified, yang berasal dari perguruan tinggi yang ternama baik di dalam negeri maupun yang berasal dari luar negeri, di mana kualifikasi pendidikannya adalah minimal S2 dan mayoritas saat ini telah berpendidikan S3.
Selain sumber daya tenaga pengajar yang berkualitas, Teknik Elektro UMY juga menyediakan berbagai fasilitas yang mampu menunjang pengembangan diri para mahasiswanya, seperti laboratorium. Laboratorium yang terdapat di Teknik Elektro UMY terdiri dari laboratorium telekomunikasi, laboratorium rangkaian listrik, laboratorium digital dan mikroprosesor, laboratorium elektronika, laboratorium instrumentasi dan kendali, serta laboratorium komputasi dan perancangan. Mahasiswa Teknik Elektro UMY juga telah mengukir banyak prestasi baik di tingkat regional, nasional, dan internasional.
Universitas Muhammadiyah Yogyakarta, Young and Global. Welcome to the Faculty of Engineering. We are part of the Muhammadiyah Development Center and play a role in the engineering field. Currently, we are developing technology and global-oriented innovation through developing cooperation to an international level based on Islamic values for the benefit of the people. Through education, we develop students to become excellent and Islamic graduates, and we do research and community service professionally. We are also a medium for students to develop an entrepreneurial spirit. Have adequate facility and professional teaching staff to support the lecture process. We will always create technology that is oriented toward the benefit of the people, to improve the people's welfare and create the developed society. The Faculty of Engineering, Universitas Muhammadiyah Yogyakarta.
Kerjain nggak sekarang? Kenapa? Kalau kerjain susah. Kalau ada gampang huruf, ya gitu berulang membuat. Iya. Enggak. Kapan? Kamu itu di bawahnya.
Good afternoon, Professor Takada.
Yes.
Very welcome to our conference.
May I check whether the screen is okay?
Yes, sure, Professor, sure. Yes, we can see the slide.
Yes. I wonder whether presentation mode works.
Yes.
So it takes some time.
Yes, Professor. Thank you so much.
Yeah. Thank you. So can you see the full screen?
Yes, Professor. We can see clearly.
Okay, thank you very much. So maybe I can keep this screen if you allow.
Thank you very much, Professor.
Thank you. Yes.
So we will open first for the first session. Then I will give you time after we introduce Professor Takada. Is it okay, Professor?
Yes.
Thank you so much.
Your Excellency, the Vice Chancellor of Academic Affairs at Universitas Muhammadiyah Yogyakarta, Professor Dr. Insinyur Sukamta. The Honorable Associate Professor Tis Dr. Wan Abdul Rahim Wan Muhammad Isa. Your Excellency, I'm sorry. Oh my God. Ada suaranya. Hello. The Honorable Vice Rector of Academic Affairs Universitas Muhammadiyah Yogyakarta, Professor Dr. Insinyur Sukamta. The Honorable Associate Professor Tis Dr. Wan Abdul Rahim Wan Muhammad Isa. The Honorable Professor Dr. Juninchi Takada. The Honorable Professor Insinyur Dr. Muhammad Rizal Arshad. The Honorable Dean of Faculty of Engineering, Associate Professor Insinyur Aris Widyo Nugroho, PhD. The Honorable Head of Department of Electrical Engineering of UMY, Dr. Insinyur Ramadhani Shahputra. The Honorable Chairperson of International Conference on Electrical and Electronic Engineering Intelligence System, or ICE3IS, Dr. Yesi Yusman. The Honorable Faculty Members and all the Committee of ICE3IS. Assalamualaikum warahmatullahi wabarakatuh. First of all, praise be to Allah Subhanahu wa Ta'ala who has given us His mercy and blessings so we can meet again in this room today in healthy condition and attend the second day of International Conference on Electrical and Electronic Engineering Intelligence System 2021 at Universitas Muhammadiyah Yogyakarta. Secondly, salawat and salam may always be presented to our Prophet Muhammad sallallahu alaihi wasallam. Allahumma salli wa sallim wa barik alaik, who has brought us from dark days to bright days. Ladies and gentlemen, on this wonderful day, please allow me to start our agenda today by reciting Bismillah together. Bismillahirrahmanirrahim. The first agenda is the keynote speech that will be guided by Mr. Widyasmoro ST MSc. Mr. Widyasmoro was born at Cilacap, Indonesia, November 5, 1983. He finished his bachelor's degree at Jenderal Sudirman University, major electrical engineering, also finished his master's degree majoring in computer science and information engineering or wireless communication at Asia University in Taiwan. And right now, Mr. Widyasmoro also lecturer and researcher at Electrical Engineering Department of UMY. His research interests in the field of wireless communication system and Internet of Things. Dear moderator, the time is yours.
Thank you so much for Master of Ceremony that introduced me very well.
You are welcome, Mr. Widdy.
So good afternoon, everyone here. Assalamualaikum warahmatullahi wabarakatuh. The Honorable Vice Rector of Academic Affairs, University of Muhammadiyah Yogyakarta, Professor Sukamta. The Honorable Dean of the Engineering Faculty, Universitas Muhammadiyah Yogyakarta, Insinyur Aris Widyo Nugroho, PhD. The Honorable Chairman of the Electrical Engineering Department, UMY, Dr. Ramadhani Shahputra. The Honorable Chairperson of the ICE3IS, Dr. Yesi Yusman. The Honorable Faculty Member of the Electrical Engineering Department, UMY. Distinguished guests and all participants of the first International Conference on Electronic and Electrical Engineering and Intelligence System, ICE3IS 2001, which held by Electrical Engineering Department, University of Muhammadiyah Yogyakarta. Once again, I would like to welcome all of you in this particular session, which is the keynote speech session in the second day of the ICE3IS Conference 2021. It is my honor to be here as a moderator for this particular session. And it is my honor also to have our distinguished keynote speaker today. The first is Professor Dr. Junichi Takada from Tokyo Institute of Technology, Japan. And the second one is Professor Insinyur Dr. Muhammad Rizal Ahmad Professor Engineer Dr. Muhammad Rizal Arshad from University of Science, Malaysia. Please, next slide. So in the first session of the keynote speech today, I would like to have an introduction for our speaker for a while. So we will have two sessions, which is first session with Professor Dr. Junichi Takada from Tokyo Tech, and the second session will be with Professor Engineer Dr. Muhammad Rizal Arshad from USM Malaysia. Please, the next slide. Next slide, please. Next slide. Yes. I will briefly introduce our first speaker for today's session, Professor Dr. Junichi Takada from Tokyo Institute of Technology, Japan. Professor Junichi Takada has been Vice President for International Affairs at Tokyo Tech since March 2019. He currently serves as a professor at the School of Environment and Society, Tokyo Institute of Technology. He received a Doctor of Engineering in Electrical and Electronic Engineering, Tokyo Institute of Technology in 1992. He served as a research associate in Chiba University during 1992 to 1994, and as associate professor in Tokyo Institute of Technology during 1994 to 2006. He has been a professor in Tokyo Institute of Technology since 2006. His research interests include the radio wave propagation for wireless communication, electromagnetic simulation technique, applied radio measurement, and radio spectrum sharing. He also involved in many projects of ICT application for the development and the engineering higher education cooperation. He is fellow of ICE Japan and a senior member of IEEE. The next slide, please. So for the this first session, Professor Junichi Takada will bring a topic presentation of radio propagation modeling of cyber physical system, road to wireless emulator. So without further ado, I will give a chance for Professor Takada to deliver his speech for about 40 minutes, and after that followed by question and answer session for all participants. Please, Professor Junichi Takada.
Thank you very much. Let me share my screen. Sorry, I had the trouble of my PC and I disappeared.
Yeah, no problem, Professor.
now I rebooted, so let me share my screen. I think you can see my screen, and I'm now switching to the presentation mode.
Yes, yes.
Okay, can you see?
Yes, Professor, we can see clearly.
Yes, thank you very much. So, good afternoon. I'm Junichi Takada from Tokyo Institute of Technology, and it's my pleasure to join the ICE3IS. This is the first occasion, so I congratulate for the launch of the conference successfully. And I'm from Tokyo Tech, and I have ever visited Jakarta once several years ago, but since then I didn't have opportunity to visit again. So today I'm going to talk about the radio wave propagation modeling in cyber physical system. The subtitle is the road to wireless emulator. So before going further about the wireless emulator, let me introduce about the radio wave propagation study, why and how, because the conference scope is quite wide, so that maybe not all of you are familiar with the radio wave propagation study. So let me explain very briefly. So the radio wave propagation in the wireless systems played a very important role because it just consists the channel response. I mean, the channel response consists of antenna and the radio wave propagation part. So, such as the power of the channel or the signal dispersion of the channel, or for the dynamic scenario, maybe the Doppler variation or the fading, such kind of dynamic behavior are all represented by the radio wave propagation. And obviously, this delay or Doppler are the source of the degradation. To some extent, antenna can control those properties. For example, introducing the diversity technique, or more popularly the MIMO technique, or for the 5G, the massive MIMO introduced the beam forming. I mean, the antenna directivity itself can be controlled in the real time nowadays. And mainly, there are two major applications of the radio propagation study. One is the channel modeling. The channel modeling is aiming at developing the standard model of the channel, which radio channel, I mean. It's used for the evaluation or the comparison of the different systems. So mainly, this kind of channel modeling is very important in the standardization, like 3GPP or IEEE 802. And in contrast, there's another very different application, that is the prediction of the radio wave propagation in the site-specific manner, which is needed for the site planning and service design. So the idea is, by putting the access point or base station, how we can cover the users. Such kind of predictions are very site-specific and totally different from the channel modeling approach. But yeah, both are important, but the majority of the researches on the radio propagation are focusing on the first one, I mean the channel modeling. And two major approaches of the radio wave propagation studies exist. The first, more popular approach is called the channel sounding, I mean the propagation measurement. So why we do the measurement? Because the individual scenarios are so complicated, so that we have to do the measurement. So the modern channel sounding consists of the MIME functionalities to know the angular properties of the propagation, and also wideband properties for the delay resolution. And for the dynamic scenario, we should also want to capture the Doppler, so that we need to accommodate such dynamic measurement. So the measurement is conducted in the real scenario. So this is if the instruments are well designed, that it's most accurate. But also it's very expensive. I mean the channel sound, the hardware. This is, by the way, the channel sound that we developed around 10 years ago for the 11 years. It's MIMO channel sound. It's so expensive. Really, it costed around 3 million US. So really, since then, we didn't have a chance to build the new channel sounders. And also, it took 3 years to develop this. Also, for the measurement campaign, it's very expensive. For example, if we are doing the over the rooftop measurement, we need a special vehicle. I mean, we call it the bucket crane. And really, just to hire this car for 1 week, it costs like 0.1 million yen. So the measurement study is very, very expensive, in particular for the outdoor scenarios. So obviously, then we think about the simulation. I'm going to explain later again, but the ray tracing simulation is getting more and more popular to take into account the reflection or diffraction, or even so-called the diffuse scattering of the structures. In particular, for the outdoor buildings, the major scatterers, and for the indoor walls or furnitures, maybe the object that we have to consider. So this solution is cheaper, but this simulation is not always accurate. I'm going to talk why it's not accurate in the next slides. So first, before going to the detail of the ray tracing, I'd like to also talk a little bit about why we do the radio propagation studies. Radio propagation sounds a little bit classical topic, but really the new use cases and new systems are appearing always in the ranging frequency. Nowadays, the terahertz is even discussed in the context of 6G, which is almost like the optical light. The bandwidth, very narrow one, I mean just like a CW signal, up to ultra wideband, I mean ranging more than 500 megahertz. Obviously, in the gigahertz band, the bandwidth is much wider. And also, the range of the Doppler spread is also very diversified. Some radios are really static, but maybe we should accommodate the communication in the bullet train with the 400 kilometer per hour with the 5G or 6G systems. And also, the different scenarios need the different studies because the behavior of the radio might be very much different. So I pick up 6 scenarios here, just which are covered as the typical scenarios in our project of this cyber physical wireless emulator that I'm going to talk next, like drone, the ITS, Intelligent Transport System, smart office, the smart factory, smart meter for the, smart city, or the beyond 5G. So frequency also ranges from VHF up to millimeter wave, almost approaching to 100 gigahertz, which is just the edge of the so-called terahertz band. And this is taken from the video. This is the video taken from our colleagues in this project, NICT. So yeah, obviously looking at all the scenarios through the videos, you can just imagine that it's hard to find the commonality of the radio propagation for the individual scenarios. So that's why we have to characterize the scenarios responding to the demand of the applications. So that's why this kind of classical study of the radio propagation is long-lasting. Because new scenarios need the knowledge of the radio channel. And also another important thing, which is related to what I mentioned about accuracy. So now the channel sounding is the best, as I mentioned, from the viewpoint that the environment, we are just measuring that environment that we are interested. So for example, for the stochastic channel model, always only the measurement results are taken into account for the standardization. There's one big reason that the prediction accuracy, I mean that even if we are using the simulations, we have the limitation of the accuracy. There are 2 sources of this limitation of the accuracy. One is the accuracy of the input model. So even if we have the very good simulator, if the environment model is incomplete, and then final result is very inaccurate. So in the case of the propagation, wireless propagation, yeah, obviously the 3D geometry has some errors, in particular for the higher frequencies. The radio wave behavior is dependent on the wavelength. So it means that the small error may result in very big inaccuracy. But more importantly, 3D geometries now we have more and more access, but still that another challenge is the material parameters. So all the structures existing in the town or in the room, they are just a mixture of different materials, and it's almost impossible to characterize electronically at very high frequency because of the variation of the materials or because of the mixture of the materials. So really, we have the limitation to input such model. And obviously, the simulation technique itself has the limitation. So in fact, you know that electromagnetic wave can be derived by solving the Maxwell's equation. So there are many accurate solvers for the Maxwell's equations, so the EM simulators we call. But the EM simulator can handle maybe tens of wavelengths, hundreds of wavelengths, but more than that, it's almost impossible because we have to discretize the space with 10 points per wavelength. That is known as the rule of thumb of the modeling in the electromagnetics. So it means that, for example, if we are dealing with the millimeter wave, it is even possible that just within 1 centimeter, we have to discretize more than 10 points. So really considering the wireless communication scenarios, the problem is too huge to model as a whole. So that is the main reason why we use so-called ray tracing simulation, that is approximation technique. So maybe for most of you who are not familiar with the radio wave propagation, you may imagine that ray tracing is the tool for the computer graphics. And really the idea is more or less very similar. But for the case of radio waves, we utilize the theory known as the geometric optics, which consider the coherent signal, which is different from the computer graphics. So the individual ray represents the propagation direction, which is the same as the computer graphics. And we look at the electromagnetic phenomena like the Snell's law of reflection and refraction. I mean that the incident wave to the plane boundary between two different materials, the part of the wave is reflected, and this reflection angle is equal to incident angle, and part is refracted, and this refraction is also dependent on the dielectric constant. Or we also consider the law of diffraction. Occasionally, it's called the Keller's law of reflection, who proposed the idea. If we have the edge, and then we suffer from the diffraction, and this diffraction can be modeled just like the cone. So if the ray is hitting along the edge of the wedge, and then the diffracted waves are propagating along the cone direction, which represent that the diffraction angle is equal to the incident angle. So these kind of mechanisms are implemented in the ray tracing simulator. But really, just after the name of ray tracing, we should trace the ray. So the most popular ray tracing approach known as the ray launching method. A number of rays are launched from transmitter, and the individual ray just process like reflection and diffraction, and finally just some of the rays approach to the receiver. So at the receiver, how we judge that the ray is arrival, and then we prepare the so-called capture circle, because the rays are discretized, and if the probabilistically the probability is 0 to hit the ray across just one point with the infinitesimal size. So instead, just considering this discretization of the rays, we consider the sphere. And once the ray is hitting the sphere, we perceive that the ray is approaching to the receiver. So this is just the fundamental ideas of the radio wave propagation, prediction, measurement, and so on. So today I'm going to introduce our recent project. It's not my project. It's a very big national project, and I'm just a part of it. It's the cyber physical wireless emulator. So first, I'd like to introduce through the video what it is. I wonder
In the era of Society 5.0, a super smart society where cyberspace and physical space are integrated, it is expected to realize a society in which various things are wirelessly connected and coordinated.
Okay.
Yes, we can.
With many
Professor.
new wireless
Yes.
devices being used, in order to make more effective use of limited radio resources, it is indispensable to develop an unprecedented verification method, in addition to the existing one of wireless systems. It is difficult to reproduce the real world and conduct large-scale verification by using existing test environments. For example, it is not possible to conduct verification taking into account actual buildings and a large number of wireless devices. In addition, field verification not only requires a lot of workforce, but also has issues in ensuring reproducibility, even if it can be done in the same location as when the actual service is provided. Since it is not possible to conduct verification in exactly the same environment due to changes in the weather condition or surrounding environment, it takes a lot of time to analyze the cause of the problem. In order to solve these problems, the use of a wireless emulator is expected. The wireless emulator is a system that enables to verify wireless devices by reproducing radio wave propagation of wireless devices and actual buildings in cyberspace. The wireless emulator enables real-time verification of a large number of wireless devices on a 3D model that emulates the real world with high precision. In addition, it can flexibly change emulation scenarios, such as adding other wireless devices during verification, and achieve low cost and smooth verification while ensuring reproducibility. A verification using the wireless emulator is expected to contribute consideration and introduction of various wireless services. For example, the wireless emulator can verify radio communication devices or radars installed in automated vehicles that require precision performance without delay. In offices where various wireless devices are used, it can conduct verification taking into account the movements of people and robots or communication capability of wireless devices. In the drone field, where it is expected to be used for delivery in urban areas, it can reproduce actual buildings or radio wave interference and verify communication performance in complex 3D environments. Moreover, it can verify wireless relay function in situations where a lot of drones fly as a coordinated fleet, such as large-scale infrastructure inspections. In order to accelerate developments of these new services and reduce development costs, the wireless emulator has currently been developed under the Ministry of Internal Affairs and Communications and will be open for use by industry and academia in the future. Society 5.0 is realized by the wireless emulator.
Okay, so this is a promotion video prepared by MIC, the sponsor of this project. And the concept of wireless emulator is like this. So this video just explains that we construct the environment in the cyberspace. And in fact, the main body of this system is that we build a virtual radio systems running on the very huge computers. And really, those communication behaviors are emulated in this realistic environment built in the cyberspace. Even more, we have the physical interface to connect the real radio systems or the prototype radio systems for the future systems. So that it's a kind of cyber physical system, which is one of a very popular topic nowadays. And we can demonstrate or we can validate whether the new radio systems work as expected in the complicated environment. So in terms of propagation, our goal is to achieve, to emulate the radio propagation of the real world in the cyberspace. So it means that it's also classified as the prediction, but different from the site planning. This is just the emulation. So how much we are able to reconstruct the real scenario in the virtual space is one of the goals. So constructing the elaborate virtual space model of the real world and emulating radio propagation channel in the virtual space, they are very important in this project, implementing this wireless emulator. And this is just the schematic view of our classical radio propagation channel modeling. So this is known as the model of Okumura, who is very famous in the radio wave propagation loss model. So usually we divide the propagation model, typically traditionally, we divide the propagation model into a few layers. But the important thing is that he had conducted a very extensive measurement, but he didn't analyze the individual scenarios, but instead, he did. He just derived the distribution, statistical distribution of the measurement data for stochastic modeling. So this kind of model is site general. So the same is the standard channel model, which I have already explained. So like 3GPP or IEEE 802, they derived the channel, I mean the stochastic channel. These models can contribute for the evaluation of the system, but really they are also built from the statistics of the many measurement data. So in other words, this stochastic model is useful to be comprehensive for the performance testing. But this itself is a kind of the fictitious model. So it's a collection of the model. So it's something reasonable. But this specific realization is nothing to do with any reality. So this is a fictitious model found nowhere. And also, this is not the site-specific, or rather we call it the site-general model. But in contrast, this kind of model is system-specific because we already have the target system that we are going to design and compare. So it means that it has some limitation about the frequency, it has the limitation of the bandwidth and spatial resolution and so on. So in contrast for the wireless emulation, what we want to do is to derive the elaborate model of the real world. So it means that it is site-specific, but system-general. So it means that we should derive this kind of the model at least applicable to the different type of systems and different frequencies and so on. So recognizing that the approach may be different from this kind of stochastic channel model. So the goal of this study is the establishment of elaborate emulation techniques for the radio wave propagation to be implemented in the wireless emulator. And for first, we need the elaborate spatial modeling like 3D building map or terrain map, or even more complicated scenarios. Nowadays, we can capture the point cloud, at least of the shape of the objects. Of course, another issue I already mentioned is that we don't know usually the material constant, even if we have the geometrical information. So the adding the electric property is essential for the simulation. And obviously, our purpose is to emulate the radio propagation, so that we need the prediction and the modeling of radio wave propagation for the given spatial model. And another important thing, which is not so clear by now, is that we should emulate a continuous dynamic channel response. Meaning that this kind of stochastic model, for example, in 3GPP, it's called the drop. So drop means it's a kind of the snapshot scenario, and for the time being, I mean, for some period of time, we can just move, for example, the mobile stations or even the environmental parameters. But really, it is relatively representing the short term because by the large moving, as I already mentioned in the Okumura model, the shadowing, I mean the cluster distribution itself may change. If you look at this scenario, you can see that if you are walking at this point and this point, where the scattering wave comes from are totally different. So it means that these are rather microscopic model for the relatively short time period of time. So we need the longer continuous dynamic channel response to construct. And to do that, we introduced two approaches, which I already mentioned. One is the ray tracing model. And the ray tracing model is to some extent accurate. I don't say it's very, very accurate, but relatively accurate prediction is possible, in particular if you concern about the surrounding object, I mean the nearby object. So within the relatively short range. But if the range, communication range is bigger, and then it may not be so easy just to run this kind of ray tracing simulation, so that we rely more on the statistical approach again, but related to the site-specific nature. So we utilize the site-specific parameters to identify these statistical parameters for the modeling. This is a little bit busy slide, but this is the whole picture of just our part. Our part means the propagation modeling part. So similarly, we have two other components. I mean the radio systems component and the emulator component. So this is really a big project. And in this propagation group, we are in 6 parties and working on the statistical model and the ray tracing model, and also the combination of these models and just to generate a dynamic response. So let me introduce a little bit more about the details. So first of all, we introduce the spatial channel model, which is independent of the system. And this structure itself is really the same as the conventional standard model known as CDL. But the difference is that because we are simulating a specific scenario, this is not stochastic, but deterministic. So it's represented by the group of rays, which are called clusters, and each ray path has some specific weight. So if we give the motion, or if we give the antenna directivity, and then we can synthesize the propagation channel. Sorry. Next. And the site-specific statistical model is something related to the conventional approach of the stochastic modeling, but it's very important to relate the geographical characteristic like this kind of 2D or 3D map, and those statistical parameters like path loss, I mean the signal strength, or spread of the delay, I mean how much the different paths suffer from different delay time, or the angular spread, how much angle range that the paths are coming. And these macro parameters are connected to the multiple cluster model. I mean that just the clusters are generated according to these parameters, and they represent the multiple propagation, which may cause the instantaneous multiple fading possibly. For ray tracing, okay, I already introduced 6 scenarios. Of course, this emulator application is not limited to these 6 applications, but at least within the project period, we are going to implement these 6 scenarios for the demonstration. So looking at the different scenarios, there are different characteristics. I mean that there are 2 axes. One is the dynamism of the channel. The other one is the range of the channel. So yeah, stationary, I'm afraid this is a picture drawn by my colleague. Maybe smart meter is almost static. In case of drone, it's still moving, but in some applications that we are interested, like monitoring drone, speed of the drone is not so fast, or beyond 5G, or and then the office or the ITS scenario. ITS scenario is most dynamic because we are going to deal with the road transportation. So the maybe you are a bit concentrated to the video, but this is a video taken from the Ministry of Land and Transportation, Land Infrastructure and Transportation, Japan, and this is really the 3D data, open 3D data available for the applications of smart city. And nowadays, we have the access to these kind of 3D models. But if we have the detailed models, unfortunately, the ray tracing simulation has some limitation that the accuracy of the modeling is not connected to the accuracy of the simulation, because this geometrical optics approximation introduces a lot of approximation and assumption. And if we introduce the detail, and then this assumption is not satisfied anymore. And the other one is, as I already mentioned, the material parameters are not attached to these 3D models. So anyway, we have to explore these material parameters to attach to these 3D models. And for the ray tracing simulation, as I mentioned, the inaccuracy is one thing, but the other thing is the computation time. So obviously, although the computation time is getting faster and faster, it is not realistic that during the real-time communication emulation by utilizing the radio equipment, we repeatedly run the ray tracing simulation. So it means that we, at least to just run the emulator system in the real time, the propagation prediction should be prepared offline. I mean that at this moment, it's impossible to predict the radio propagation in the real time. So our idea is that we store this propagation characteristic in the grid, and within the grid, we are going to interpolate such grid data. The other one is the treatment of the dynamic objects other than the radios. The radio motion of the radio equipment itself is modeled as the spatial distribution, so that we are able to deal with. But the third object moving around, like in the ITS scenario, the other cars, we need to model separately. And for the modeling of the signal transmission, I mean the radio signal transmission, we are introducing the very typical model, so-called the SOS and TDL model. So it looks a bit complicated, but the idea is very simple. This right picture is called the sum of sinusoid. So it means that individual inputs represent the rays. And the rays suffer from different Doppler frequencies depending on the direction, so that by rotating the phase separately, the final summation may result in the superposition or the cancellation, means that it's a kind of dynamic fading. So this sum of sinusoid represents one cluster. And this one is the tapped delay line. And in fact, this sum of sinusoid output is input to the tap coefficient. So the X is the input and suffer from the different delay time. And the individual cluster has the individual delay time, so that the delay component is again suffered from the multipath fading, which is dynamic. So at the receiver, such summation is observed. So this model just represents this CDL model in the signal domain. And as I mentioned, the ray tracing is difficult to run for the continuous space and in the real time. We decided to attach the channel parameter, I mean the CDL parameters to the individual grid. So the individual grid has the specific CDL parameters. So once we start the emulation, for example, by moving the receiver, the mobile terminal, and then we interpolate the channel response from this grid data at some certain point. If it's moving, this interpolation is just updated instead of repeated running the ray tracing. So by doing that, we are going to emulate the channel almost in the real time. So in the current schedule, at least we have to complete the initial implementation and the first demonstration of this system. Unfortunately, today I just talked about propagation, but the whole system of the emulator is now in the preparation stage for the initial implementation for the testing and demonstration. And within half a year, maybe we are able to show what was implemented. And our partner, the National Institute of ICT, NICT, is going to open this platform for the research purpose. So not only within Japan, but internationally. So maybe in near future, you can even access this kind of platform for testing your radio systems. Okay, so that's all for my today, and thank you very much for the attention.
Thank you very much for Professor Junichi Takada for the presentation. It's a very excellent presentation and it's very insightful for all of us. And now I think we just directly go to the question and answer session from the participant. So far we have about 50 participants here. So please, if you have any question, you can just directly use raise hand feature in the MS Team, and you can directly ask your question to Professor Takada. Otherwise, maybe you can just type your question in the chat box, then I will read for you. Okay, so maybe for open the question and answer session, I will have one question, Professor.
Yes.
It's very interesting topic and it's very new, I think, very new topic in this wireless communication and propagation. So as we know, we only so far we only have like a simulation that it's very generic and it's not specific, and you introduce us about the emulator that will work for a very specific area. So it means that if we implement in the urban area, we have to like model all of the city, like Tokyo, for example, or in Indonesia, maybe Jakarta, something like that. It's very difficult, Professor, to simulate all of the city.
You're right. Yes. So yeah, thank you very much. It's a very important question. I totally agree with you. And yeah, obviously it's impossible to implement such big areas. So as I mentioned that okay, maybe I forgot to mention. Sorry, I share the slide again. There's some problem with sharing the full screen. So let me just use this screen now. So as I mentioned, we just do the emulation, but I forgot one thing. Although I mentioned that yeah, we need the dynamic emulation for some certain period of time, we have to prepare the detailed scenario, including the environment and also including the individual motion or even to describe about the individual communication systems behavior. So just to write such kind of scenarios, usually the range of the coverage area is limited in nature because of the computational resource. So obviously the whole Tokyo is almost, of course, impossible. So for example, for the cellular scenarios, now we are considering just with But by using supercomputer, we can just emulate within such kind of range.
Okay, so it means that if we build the emulator, so we have to like take the use case for specific area in the city, for example, something like that. Like, okay.
Yes.
Because it's difficult to emulate whole city.
Yes.
Yeah.
And also, as I mentioned, that really emulating itself is very difficult, but as well, preparing the data to feed to the emulator itself is also very, very difficult, I think. Yeah, huge
So,
information we need to input. It means the huge information we need to collect.
Yeah, but it's the goal is very nice and very good, Professor, because the current system that we use now, the simulation is like a generic, like yeah, it says generic, and it can apply it for a whole city. So, but it's not accurate. Yeah. and how about like this, Professor? Because I have like very interested in this topic. How about like the correlation between the like prediction, channel prediction in indoor and outdoor in this simulation, Professor? Because outdoor and specific indoor also different, like in the office, in the like subway and everything. So do you consider to make the emulation and have a connection indoor and outdoor radio wave propagation, something like that, Professor?
Right. Thank you very much. Yeah, this is a very important question. And in fact, this is one of the most challenging part. And at this moment, we didn't start to work with, but yeah, obviously the connection between indoor and outdoor is one of the topics that we should deal with maybe toward the end of this project. So at this moment, I just assume that we are doing either indoor or outdoor. But obviously, considering the emulation of the human behavior, we should integrate those scenarios finally. Yes, but as I mentioned that by doing that, we need to integrate also the 3D models dealing with outdoor and indoor together. And I feel that is also challenging.
Yes, it's very challenging project.
Yes.
Even in specific indoor, will have the different modeling.
Sure.
Right, Professor? Yeah, like subway. Subway in Tokyo will be different, like subway in Jakarta. So the modeling is very very specific area.
You are right. So yeah, obviously the aim of the emulation is to deal with the very specific areas, just like Jakarta subway or Tokyo subway. But at the same time, it means that we need to prepare the 3D data for Jakarta subway and Tokyo subway separately. That is really challenging. So that's why I put this 3D modeling also as one of the research topic, because it is not trivial to collect such 3D model. Of course, the constructing company have the drawings, but they are not drawn for the radio emulation. So really, we still continue the discussion how we import such kind of data. But at this moment, it's far beyond the applicability. So yeah, I also shown about this plateau. This is the Japanese government initiative of the virtual city. And they also collected the huge amount of the data of the townscape in not only in Tokyo, but several towns. We have the access to it, but at the same time, we feel that to make this running on our emulation, also we need a big effort. We are trying to deal with this model in our emulator by the end of this project, but it's also challenging.
Yes. Thank you very much, Professor. It's very huge project and many challenges.
Yeah.
But the goal is very excellent.
Yeah.
So I will let the other participant, maybe if you have any question, please. It's very interesting topic in the wellness communication and wellness propagation. Maybe any question? Oh, I would like to welcome Dr. Fu from MMU that joined in this session.
Thank you very much.
Because
thank you, Prof. Nice to see you.
Yeah, so welcome.
Thank you.
Thank you.
For inviting us. Thank you.
Yeah. Do you have any question, Dr. Fu?
I'm sorry, I joined the talk late, so I cannot ask any meaningful question now. I'm so sorry. Sorry about it. But it's very nice to see
Yes.
Prof. Takata's presentation. Yeah.
Yeah. Thank you very much for your participation.
Thank you, Prof. Nice to see you again.
Okay. Any question from other participants? Maybe from Dr. Yesi. Any question?
Okay, Prof. Takata, so far, is there any collaborations in this project with other universities, for example, other universities in other countries?
Yes. It's a good question. So in fact, this is a national project and all the partners are in Japan at this moment. And yeah, relatively speaking, that it is, yeah, I shouldn't say the limitation, but because of the government funding, the international collaboration can be integrated, but not aiming at. So, but as I mentioned, in particular, we invite the users of this emulator at the end. So really, we are exploring the collaborator, I mean the users, potential users for the future.
I wonder, is there any similar emulator worldwide outside Japan?
Thank you very much. Yeah, it's a very important question. I am sorry, I skipped about it, but really, at least in the United States, the Department of the Defense introduced something similar in the past, but much more primitive. So at least our colleagues inspired with that. But then they recognized that even before that, in Japan, there are another researcher who developed this kind of system. I mean, the concept of these systems. So really, maybe there are some similar ideas in other places. But this project itself is very big compared with those existing ones. In particular, in terms of propagation, nobody tried to derive very realistic propagation characteristic, but just introduce some empirical equations like Hata or Hata.
Prof, what about the research effort in Europe?
In Europe, I haven't confirmed, but yeah, I've heard that there are some small initiatives similar. So I have to examine about such activity. Yeah, but it could be possible that in Europe, because in particular in Europe, the propagation study is very active. Not only propagation, but virus study as a whole is very active. I should check it.
I think because the cost is very huge also, Professor. So not many company or government try to do that.
Could be, yeah. Really, this is a big project, and yeah, without government funding, it may not be so easy for us to work on this kind of very challenging project. So it means that we also have a lot of pressure from the ministry for the success.
Yeah. So, Professor, I have one other question. That if the emulator is already ready just in the first stage maybe. So can like public to access that kind of emulator, or it just for like government use, or maybe industry only, or
Okay, it's a very good question. And in fact, maybe the initial implementation is just a demonstration, and it's not yet so flexible. So it just runs on our scenario, I guess. But for 2024, I mean, at the end of this project, we are targeting that we are going to open this to the public access for the researchers and engineers to test their own ideas. So very probably you'll be able to access this system 2.5 years later.
Oh, very nice.
Yeah.
Dr. Fu, you have any other question maybe? Or maybe Dr. Jesse Jusman?
No question, Bapak.
Okay. Dr. Fu, maybe?
Prof, will the emulator be free, and is it like a standalone version that we download the emulator and then use it on our locally in our own computer?
Yeah, in fact, this is not a software emulator. In fact, this is a cyber physical system. So it means that we provide the access doesn't mean that we distribute the program, because really this is a very huge cluster computer, and also the hardware. I mean, the very high speed RF circuits implemented to connect to the physical radios. So obviously, just for the virtual part, maybe the remote access is possible. But once you are going to integrate the physical radios, so obviously you should come to Japan to test. And yes, I should say that for the cost, nothing is decided, and unfortunately, it's not my matter. So it's the matter of NICT. I mean, the project leader, and now they are just arranging how much the cost they are collecting. Yeah, obviously this software is also customized for their computer system, so that it's really the system combined combination of the computer and the software. So that's why we don't have the idea to release this software to other parties. But at the same time, for the access, very probably for the research institute and the universities, they will offer the access with free of charge or very low price. For the industry, I think they plan to charge more, but I'm not sure how much.
Okay. Okay, thank you very much, Professor Junichi Takada from Tokyo Institute of Technology, for your excellent presentation, and it's very insightful for us. Since we have very limited time, so maybe yeah, next time we can have other discussion and to follow up this kind of research.
Yes,
it's very interesting.
Thank you.
Thank you so much, Professor Junichi Takada, for your attendance and for your answering all of the questions from the participant. It's a great pleasure for us to have you with us in this session, Professor. Thank you so much.
It's my pleasure also. Thank you very much.
Thank you very much, Professor.
Yeah, in fact, this is my first occasion to present this idea outside Japan.
So maybe next time we can have like invite you directly to Indonesia, to Yogyakarta, Professor.
Oh, yes. Thank you very much.
Yeah. Okay. Thank you so much, Professor Junichi Takada, and thank you so much for all participants. And now we will move to second session for this keynote speech session this afternoon. We already have with us Professor Insinyur Dr. Arshad, Muhammad Rizal Arshad with us. Good afternoon, Professor. Professor Muhammad Rizal Arshad from University Science Malaysia. Good afternoon.
Yes.
Nice to meet you this afternoon.
Is my voice clear?
Okay.
Suara saya jelas?
Yeah, clear, Professor.
Okay.
So yeah, before we begin the presentation session for Professor Muhammad Rizal Arshad, I will just read a brief introduction for our speaker for the second session. Professor Rizal Arshad graduated from the University of Liverpool, UK in 1994 with a Bachelor Engineering in the field of Medical Electronics and Instrumentation. He then pursued his Master of Science in Electronic Control Engineering at the University of Salford, graduating in December 1995. Following from this, in 1996, he continued his study with a PhD degree in Electronic Engineering with specialization in robot vision system. After completing his PhD training in January 1999, he started working at University Science Malaysia, USM, as a full-time academic. He has supervised many postgraduate students at the MSc and PhD level. He also has published actively in the local and international publication. He is currently a full professor at the School of Electrical and Electronic Engineering, USM, from 1st December 2019 until 28 August 2021. He was the Deputy Vice Chancellor in Academic and International at the University of Malaysia, Perlis. Prof. Rizal is a professional engineer and technologist and is well known as the pioneer of underwater system technology and robotic research effort in Malaysia. Professor Rizal is very interested in investigating the fusion of the natural world with the modern engineering pool of knowledge. Next slide. For today, his topic presentation is about robust autonomous marine robotic technology for real-world application. So, without further ado, I will just give a chance for Professor Muhammad Rizal Arshad to present his topic and followed by question and answer session later on. Please, Professor.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you to Mr. Johnson, Dr. Widya Moro. I'm sorry if I kalau silap sebutnya. Thank you very much to Dr. Yesi Jusman for inviting and the team for inviting to this international conference on electronic and electrical engineering and international intelligence system. So I would wish that I can be there physically, but of course we can't for now. Inshallah, maybe in the future. So let me share my slide. How do I share my slide? Let me just wait. I should be able to share my slide, right? Screen, Windows. Okay. Okay. Can you see my slide? Can you see my slide or not?
Yes, Professor. Already.
Yes.
Yes. Yeah.
Okay. So I'm now based in University Science Malaysia in Pulau Pinang on the northern part of Peninsula Malaysia. So my topic today is robust autonomous marine robotics technology for real-world applications. So my team, we have been working on ocean or marine robotics projects since year 2000. So this would be around 21 years plus that we have been doing this research. And we have basically developed, focused our attention to robotic system application for marine environment because there are a very limited number of robotic research who who have focused their research on marine applications. I have a number of colleagues from Indonesia. I think I work closely with our colleagues from ITB. Also, we work with ITS. In Singapore, we work closely with our colleagues from NUS, NTU, and we have also our linkages, link in China, in India, and also in Europe. Of course, we have colleagues in the US that works on the same area. So basically, the objective of the talk is to introduce the field of unmanned marine robotics, covering autonomous surface vessel, or we shorten it to ASV, an autonomous underwater vehicle, or AUV, we call it. I think I just want to highlight the difference between AUV and UAV. I think nowadays the drones or the UAV, what we call an unmanned aerial vehicle, are more popular, the term UAV. But when you talk about AUV, this is referring to robotic system drones that is used in marine or underwater environment. So we call it AUV, autonomous underwater vehicle, which are utilized for many robot industrial and hopefully for and some are in scientific applications. I would also like to basically share some of the basic modules of ASV and AUV platforms to share some applications of these two types of marine robotics, and also to discuss the potentials of ASV and AUV technologies in the future. So in terms of marine robotics, as a robotic person, we are a system integrator. We are the enablers, the enablers between the application and the technology, and also the techniques of in terms of the science and the technology and the application. Roboticists are the system integrator. So we develop basically system that can solve a number of real applications, not just limited to those demonstrated in the lab environment. This is talking about real applications. So you can see for ocean robotics or underwater robotics or marine robotics, there are many applications. Then these are among the 6 major kind of sub field of applications. In science, there are many urgent needs for seafloor mapping, or for rapid response to oceanographic and geothermal events. For example, when there are earthquake where the source is in the middle of the ocean, for example, you need to send robots to go and map the area to see the bathymetric or the ocean floors, changes to the ocean floors, for example. So for science application, we talk about geological sampling. For environmental application, we talk about long-term monitoring of, like, say, oil spill, hydrocarbon spill, environmental remediation, etc. Even inspection of underwater structures, for example, we have. Sorry, sorry, my daughter just joined our talk. Sorry about that. So there are many applications for underwater structures, military application, oil and gas, etc. So all this needs a robotic application. I think I just want to highlight the point that Malaysia and Indonesia are among what we call a maritime nation. We are a maritime nation because the sea area, the marine area, we are surrounded by water mainly. But like Indonesia, we know that Indonesia have around 19,000, 17,000 or 19,000 islands, for example. So this is similar like Malaysia. We have, of course, much smaller number of islands, but there's a lot of applications in terms of the oceans, and we need the technology. And for your information, in terms of, if I take just an example of seafloor mapping, only less than 10% of the seabed have been mapped around the world. Earth is 71% covered by ocean, by water. Only less than 10% are properly mapped. The seabed are properly mapped. Of course, if you open up the Google Earth, you can see all the seabed maps. If you go to even to the middle of the Pacific, you can see some ridges at the bottom of the sea. But those are not actual data from on-site data. Those are what we call a magnetic spread of the Earth's surface, into magnetic strength spread across on the Earth's surface. So that's why we still need to go to the ocean to do mapping. So if you remember, many years ago in 2014, if I'm not mistaken, when the incident of MH370, where the Malaysian aircraft was assumed to have crashed in the southern oceans, that was at the average depth of around 6,000 meters or 6 kilometers. And we know that area has never been mapped by anybody. So it was a challenge, and even to this day, nothing has been found in terms of the wreckage, etc. So the point is, the ocean are so vast. We can't, and there's so many things have not been explored, yet to be explored in the oceans, and we need technology, robotics technology, which are robust in order to withstand the ocean environment. The ocean environment are very corrosive because it is, very high acidity. It's very rough. If you put like metal, it can get corroded very fast, for example. So that means, and we would like, when we explore the oceans, we wouldn't want to endanger human lives. We do not want to send human down into the oceans. And just to share with you, I've mentioned to you that more than about 71% of the Earth's surface are covered by water, and the average depth of the ocean is around 3,800 meters. The average depth of the oceans, and if we know from the literature, the deepest, even the best modern nuclear submarine, they only dive basically maybe around 500-600 meters. That's the max, because they call it the crush depth, the depth that they cannot exceed. That means even the best modern nuclear submarine do not go 1,000, 2,000 meters. That means there's a lot to be discovered down there, and in the future, scientists and researchers, they have projected that in the future we have to go to the oceans to get our source of energy, in terms of minerals, metals, in terms of even water, of course water, but fresh water source, even so many food, etc. We have to go to the ocean. That's why many countries around the world have started to invest a lot of budget into ocean research, and one of the important area of research is robotic research, to develop, for example, machines. For example, just an example, like deep water mining, robotics modules that can go down to, let's say, 5,000 meter or 6,000 meter kind of water depth. So there's a lot of applications in terms of robotics, and it is not easy, because the deeper the water that you want to test, to explore, to do research on, the more challenge in terms of testing, in terms of launching a recovery. So there's a lot of issues when you talk about it, but the potentials are big. So in terms of evolution of marine robotics platform, before this, most of it, in terms of maturity, ships, technology ships, that means manned ships, are very mature. You have various size, various shapes, the amount of payload it can carry. But in the future, people talks about unmanned ships. That means, for example, tankers. We know that, let's say from Selat Melaka, if you go to Malacca Strait, Selat Melaka or Malacca Strait, easily you have 100 or 200 tankers. We ply the route every day, and these are big tankers. And the future is the possibility of making this unmanned. That means the tanker is unmanned. All the ships are unmanned, so we can always we can automate in terms of its movement, motion, etc. So then we talk about, there's a lot of technology involved when we talk about trying to deploy a robotic system into the oceans. So you talk about in terms of autonomous navigation, talk about robust sensor modules, talk about AI in AI in terms of path tracking, in terms of identifying obstacles, and ocean or marine environment are very interesting. I say interesting, actually very challenging, because it's different. If let's say if you are moving on a ground, the ground will not move. It's fixed. You are moving. But when we are deploying our robot platform in the ocean, everything is moving. Our robot is moving, the environment is moving, and you have, for example, you have lateral wave pushing your craft in the water, etc. So, and if I give you an example, if I do research in UAV drones, if I fly my drones, aerial vehicle, I can see, let's say 1 kilometer, 5 kilometer, I can still see visually my drones. But if you do ocean robotics, it swims more than 30 meters, you cannot see it at all. It is totally blind, so you cannot see the system. So it's very challenging in terms of localization, for example. You want to know where is the robot. For some of us who do robotic research, we know in robotics research, there's two big questions, which is for autonomous robot or for mobile robot, the system will ask you, where am I? Where am I? That means, where is the robot? That means you talk about the problem of localization, how to localize the robot. Where is it? In the air, in the water, in the forest, for example. And the second question is, where am I going? The navigation. So the robot needs to we need to supply the information. Where is it going? Okay, and the robot, bear in mind, the robot will not ask you, who am I? Who am I? The robot won't ask you, who am I? If the robot asks you, who am I, you're in trouble. So that means the robot will ask you, where am I? And where am I going? So it's localization and tracking, or localization and navigation. And in the ocean, it is very challenging because there's no GPS. There's no GPS. You have to have acoustic. As of today, the mature technology is to use acoustic-based GPS-like localization method. That means you have beacons, you have listening posts, let's say 3-4 listening posts, and you have your robot giving beacons for it to localize, or vice versa, the other way around. So you need to localize where it is in the water. For information, if you have, let's say, I'll give you an example. For example, Java Sea. Java Sea, the average depth at the deepest point in Java Sea is around 100 meters. Java Sea is not deep. That's why, so let's say South China Sea also. South China Sea also not deep. The average depth is around 200 meters. It's not deep. The deeper part is the ocean, like the Indian Ocean, the Pacific Ocean, Atlantic Ocean, etc. Those are in the thousands. For example, like the average depth of the Indian Ocean will be around 3,000 plus meter, or 3.5 kilometer and onwards, and the depth. And the penetration of sunlight into the seawater maximum is around, I would say, in our water, the hotter climate probably is around 60 meter of 30 meter, 40 meter. Then it becomes pitch dark. That means there's total darkness. Imagine if you try to navigate your autonomous robot at a depth of 2,000 meters. There's no light, so there's no, and in water, the water columns means at the surface until to the seabed. The water columns, it has different layers of temperature, salinity level, and also density. So this will affect I managed to listen a bit the previous presenter on ray tracing. If you do ray tracing, for acoustic ray tracing, it won't be in a straight line. it will bend and curve according to the layers. So that makes your localization prone to errors. So that makes your localization of the robot very tricky. So that means in order to navigate your underwater robot in the deeper water is going to be very challenging, because your localization also have inherent error compared if you use satellites. We know that if you use GPS, if you have 2 GPS, you can't. You can't localize. You have to have 3. And nowadays, if you have a clear sky, you may have, let's say, 10, 15, or even 20 satellites to make your position very accurate. Not so in the water, because because in terms of the localization beacons is much less. So this is a challenge, the challenge of autonomous navigation, and now we are talking about swarm intelligence. So these are some of the topics which is the upcoming topics in ocean robotics. I think swarm intelligence, if you go and Google swarm intelligence and robots or robotics, or robots or robotics swarm intelligence, there are so many papers on mobile robots, on land mobile robots, and also aerial. But now you will start to see papers for ocean application. So these are some issues regarding application of robots for the oceans. So let me give you an example of why it is important for us to do research on the oceans. We talk about global warming. We talk about how ocean play a role in the carbon cycle, for example. Ocean is the biggest absorber of the carbon dioxide in the environment. It's the biggest absorber it absorbs, it gets the carbon dioxide in the environment out from the air into the water. And that will basically reduce global warming in terms of marine pollutions, in terms of fish stocks for food supply, for example. And also we talk about impact of anthropogenic noise. Anthropogenic noise means noise which are made by human, for example, from drilling, from shipping activities on the ocean fauna, or the living beings in the oceans. This needs studies. And also, for example, gathering data for the oil and gas sector. What I'm saying is that the ocean throws a lot of problems and applications that need to be solved, but we need to get the technology. And the technology, that one of the pertinent or important technology is a autonomous robotic technology for the marine applications. So you have, for example, you have to measure the signal, measure the environment, you have to monitor, and this will enable us to manage the environment. Okay, autonomous vehicles are now getting used to, when we want to do surveys of the oceans, we use ships, manned ships, with crews, many of them on board and out into the oceans. But now people have started to move away from it and start to send autonomous vehicles into the ocean. And this is where we have advantage, because first, the robot can be out in the ocean longer, for weeks, without having to return to port regularly. It is safer because there's no human on board. So this is why nowadays you will see that these are examples of autonomous unmanned surface vehicle, or what we call, some people call USV, or some people call ASV, unmanned or autonomous surface vessels or surface vehicles. So these one are, I'm not sure you can see it, these are produced by, the first one produced by called Autonaut in the UK. This is wave powered. It moves by the wave energy, not by propeller. It by wings, by fin. Then you have the wave gliders, and you have a number of many different kinds of autonomous surface vehicle or platforms. And these are examples of the whole array of autonomous vehicle by the National Oceanographic Centre in the UK. So these pictures are old pictures. I think this was taken maybe around 2015 or 2016, about easily 6-7 years ago, and already they have so many ocean-going fleet in order to get data of the oceans. And the bottom part here, I'm not sure you can't see my mouse moving, but anyway, the many yellow torpedo-shaped craft in the middle, those are what we call an underwater gliders. And the same also at the three yellows and the one like purple colored, those are also underwater gliders. Underwater gliders are the type of underwater vehicle that can be sent out in the ocean to do measurement. They can stay there for 1 month, 2 months, 3 months without having to recover, and they are continuously collecting data. So these are examples of, and you can see at the back the big torpedo-shaped vehicle. Those are called auto-sub. These auto-sub are used to under ice mapping, which is in the Arctic. The UK, they use it to do under the Arctic shelf, ice shelf. They send the auto-sub under it to do mapping of the seabed down there. So this is important, because only when we have enough information that we can do a lot of things. If you don't have enough information of the ocean, we will certainly limit what we can do with the oceans. Okay. And then you have the unmanned surface vessel, and this has began so many years ago in the 17th century. You have late 17th century until now, people have developed many kind of floating vessel. So you can see craft. Okay, you can see different kind of craft, right? So, like including canoes, etc. But now we want it autonomous. We do not want to put human having to paddle it or something. We want it to be autonomous. That means it moves by itself. You can control it. So now when you want to make it autonomous, we have to talk about power issues. How can we communicate with it? How we can control it? What kind of material that we can build it from? You know, when you put a boat, a robotic boat out into the ocean, what happens is that after it is out in the ocean, let's say for a month or two, barnacles, what you call it, barnacles or shells will start to develop on the side, on the walls of the boats. This will basically affect the sensors, the integrity of the boat itself, the autonomous boat. So we have to, for example, have to design, use material which is anti-biofouling. That means it prevents microorganism growing on the walls, for example. So there's a lot of issues when you want to make something autonomous or unmanned, and it stays very long, let's say in the oceans, out in the oceans. Okay. So it talks about, there's a lot of technology that needs to be considered when we talk about autonomous vehicles. And this does not just apply for ocean going. It also applies for land robot or flying robot. For example, in my lab, we also develop like mobile robot, wheel robot, or track robot for land application. We still have to talk about communication, about cost of computing, about localization problem, navigation, sensing. Same problem. It's just the environment is different. If we develop robot for the oceans, you have the water issues. The water have hydrodynamic drag, etc. If you develop for the flying vehicle, you have the issue of weight, payload. If you develop something for the land, mobile, so you have to consider the wheels. What kind of wheels? What kind of do you have trees in front? Do you have incline? Is it going up or going down? How steep it is, for example? Is it sandy? Is it rocky? Is it muddy? So these are a lot of issues which is applicable to any autonomous vehicle system or projects. It's just the different environment will affect or will influence our design of the vehicle. Okay, So currently for ASV, or autonomous surface vessel that goes into the oceans, these are some of the most common one. You have the autonaut, you have the wave glider, you have sea glider. There's another one called sea glider, slocum, etc. Those are different name of or different type of surface vessel. So you can see here on the image, different kind of seagoing, or each one of these. This is unmanned, autonomous. It is being controlled by using satellite, and it will move independently out in the open ocean to measure. Depends on the kind of sensor that we put on it. Some are measuring temperature, some are measuring the salinity, chemical pollution, etc. There are sensors that you can put on the robot. Okay. So you can see there's a whole range of different kind of robot for the oceans. For our waters meaning like Malaysia, Indonesia, around this region, it is shallow water. Shallow means less than 1,000, less than 200, 300 meter depth are considered shallow. Of course, it is not shallow. Just to give a matter of scale, the ocean depth is that if you put the Mount Everest around 8 point something kilometer, and the deepest trench in the ocean is around 11 kilometer, which is the Mariana Trench. So that means the oceans are very deep. So there's a lot of craft that people use. This is all these are all on the surface, but there are some which are semi-submersible. That means some of it is in the water, some of it on top. But all in all, this is floating. This is not in the water. But there are many applications that people are now using it. For example, if you can see, there's a boat here on the, I would say on the top, on the right side, the black boat. Those are autonomous. That means people are using it for border protection, border inspection. If people want to break into the border, through the border, you can control it from land. So this is out in the sea. Okay. But just one of the major way forward that people have developed for ASV, or autonomous surface vessel, is the use of wave power. Wave power means you don't have propellers. It is using the wave energy, which is because we know that we want, when you have a boat, you want it to move forward or left or right. And what you have is a wave energy which is moving up and down. In most of the time, it's up and down, the wave. So the whole key concept of wave energy is to convert the rate of motion on the vertical motion and convert it to lateral motion. So this is where they use fin at the front and the back side in order to harvest the wave energy to move the platform. So these are some examples of how people harness the wave energy in order to power the unmanned vehicles. So two of the major platforms that use the wave energy is what we call the autonaut and the wave glider. I'm not sure if I can, if I click here, or cannot. Okay, okay, can you see it? Can you see it moving? The video is moving? Yes? Okay.
Yes, Professor. Yes.
Okay. So this is what we call a wave glide autonaut. So you can see the front fin and also the back fin. This is so it is, there's no propellers, there's no rudder, there's no motor or rudder, blade or something. This is purely utilizing the wave and the fin in order to push it. So you can see the fin at the front part and the back part. This fin is harvesting the wave energy to propel the boat forward. So these have traveled the Atlantic, the Pacific, crossing hundreds of kilometers of water, and while it travels, it measures a lot of data. So you can see here. So this is in a lab. This is a tow tank. This is a this is where they test it. So sorry. Okay. Sorry. Okay. You can see, and this is the example of so basically what they have at the front and at the back is just a fin. So this is example of autonomous surface robots which can be deployed out in the ocean for many days, for weeks, for months. So you can see here in terms of the basic sub-modules, it's just the same as in any autonomous robotic module. You can see there's a control module, there's a communication module, there's a power module, there's a sensor module, and also there's a mechanical design itself. And also you have the payload. For example, this autonaut robot is very interesting because this middle part is the payload where it can extend and you can add more payload. That means if you have more sensors. So this is just an example. And this is another one, what we call a wave glider. A wave glider utilizes the same concept of, so if for autonaut, it hovers on the water surface, but for a wave glider, the top yellow part is, whereas this one, there's a cable, tethered cable, and this is the wave engine. That means it uses the vertical motion of the inside water to convert it to a forward motion. And you have the rudder to change left, right, to change the direction. So this is an example of, so this is the actual, and these are the actual applications that they have. And what they have here is that this bottom part will pull another, this is a sensor module in the water. So you can see quite interesting utilization of the platform. So then, of course, you have underwater gliders, and these underwater gliders. So I can go on and on. My point is that people have now, researchers have now ventured into developing long-term deployable kind of robotic solution for the ocean. Because why? Because if we use a ship, you can't deploy a ship for a month or for 2 months because you have human and it open up a lot of risk to the human operators. But when we send robots like this, it can operate even in tornadoes or in heavy typhoon because it's just a small craft and it can endure all the weather challenges. Okay, so so you have underwater gliders, and these are some of the things that we have developed in.
Sorry,
yes.
I'm sorry, Professor. Maybe we have another 5 minutes for presentation, and we'll continue for the question and answer session. Thank you.
Okay. So these are some of the, if I can just click here. So these are some of the things that we have developed a number of years ago. So what we have is that we have, this is a floating craft that we do to measure our lakes, the depth. So we test it. This is in our swimming pool in the university, and then we test it in the actual lake. And all this craft are having echo sounders. It measures the depth of the lake, and then we consolidate all the information, and it gives a bathymetric lake bed kind of contour. So this is an example. Then we develop a very small ROV, remotely operated vehicle. This is for simple shallow water inspection. So very simple kind of robot. The one, so in here you have the cameras, you have the sensors, you have the, so this is to do inspection of like ship hull inspection, etc. So if I can just fast forward. Okay, and this is what we measure. We measure under the ship, the body of the ship. We want to measure in terms of the anode, etc. And we develop also micro autonomous underwater vehicle. This is where we try to use a very small. This was a testing phase. in the pool. So you get some. We're just trying to explore in terms of propulsion, etc. So what I'm saying is that sorry. Okay. So there are many applications of USBs and ASBs. So the point that I want to make is that the robotics, those who do robotics for land application, they can easily migrate to the ocean application because the submodules is just the same. It's just they need to be get used to the environment that they want to put their robot in. For example, in terms of enclosure design, you want to prevent leakage, for example. If you want to put your robot in the ocean, you need to talk about how long can the battery be active or is on, is high before it goes out. So you need to recharge it. So these are the issues, and it needs to be able to navigate its path and not colliding with other ships or other vehicles, for example. And there are many applications for ocean robotics. So what I'm trying to highlight today is that autonomous surface vessel and autonomous underwater vehicles have a very wide application in the oceans, and there's a lot of technology involved in developing and deploying this in real-world applications. And we hope soon we're going to have a fleet of this, and we can do a lot of we provide real solutions for the industry, also for the users out there. Okay, I think there's a number of things I want to show, but the point is all this needs robotic solutions. You can't go on ships no longer. You need to go to use robotic solution to do all this. Okay, so if I can just conclude. Okay, so the whole point of using robotic solution is to address the issue of measure, monitor, and manage. You need to measure, be able to measure your environment, to monitor it before you are able to manage it. So I always call it the 3M approach. So autonomous vehicle, autonomous surface vessels are needed because this will help us to solve a lot of issues that we are facing. So I think I hope you have learned something, or you've gained something out of this short presentation. And I hope in the future we can collaborate. I can collaborate with some of you on a number of projects. So I know we are running out of time, so I thank you very much for your attention. And I'm sorry my daughter burst into the room just now.
It's okay, it's fine, Professor.
Something I would like to say Assalamualaikum warahmatullahi wabarakatuh. I return back to you.
Warahmatullahi wabarakatuh.
Thank you so much, Professor Dr. Muhammad Rizal Arshad from USM for giving us new knowledge and share with us his expertise in the robust autonomous marine robotics technology for real-world application. So we will continue for the question and answer session. You have time to just ask directly by raising your hand in the MS Team feature, raise hand feature, or maybe you can ask through the chat box. Then I will read the question for you. So please, if you have any question, the participant. Yeah, Dr. Yesi Jusman, please.
Assalamualaikum warahmatullahi wabarakatuh, Prof. Rizal.
Assalamualaikum.
Terima kasih sekali Prof atas kunjungannya dan kehadiran di Universitas Muhammadiyah Yogyakarta ya Prof.
Terima kasih Dr.
Prof Rizal adalah profesor saya dulu di one of profesor saya yang ada di Departemen Electrical and Electronic UMY waktu saya S2.
Ya, sama-sama masih muda masa itu.
Ya, Prof. Waktu dulu itu saya sangat terkesan oleh riset Prof ya, tapi itu bagi saya mungkin agak terlalu sulit gitu. Robot dan hubungannya dengan software. Jadi saya belum mengambil untuk itu gitu ya. Nah, Prof, saya mau bertanya Prof, tadi I want to ask something about the research. I hear that marine research Prof. Rizal. How about using the deep learning, Prof, for the detection in the research, Prof?
Yeah, yeah.
Is it possible, Prof? Possible, Prof?
Yeah, it is. I have one PhD student who already graduated. His name is Dr. Faid from University Technical Melaka, UTEM, if you know UTEM in Melaka. So he used deep learning in order to we have the autonomous underwater vehicle. This robot yang bergerak sendiri, dia for docking, underwater docking. So you have the docking station. And he uses deep learning in order to identify the marking to dock. Faham ya? To dock the AUV into the docking station, because there's no way it will communicate with satellites.
Just on the water.
On the dive.
I see.
So it does based purely on gravity and change of the buoyancy. So it changes the center of gravity so that the robot will tilt, and then it the buoyancy become negative, that it will drop. So as it drop, it will measure. Then as let's say you want it to dive, let's say 3,000 meter, 1,500 meter, for example, it will start to change the buoyancy positive. It will start to go up. So while in the water, there's no. Why in real underwater glider, they will only measure the waypoints, the points at the surface. Now in the water, they will not be able. They will infer the location based on depth and also some underwater localization. But most of the time, they only measure the point on the surface. So every time they are in the surface. Some robot will stay for not more than 15 minutes because of it's open water. So normally 15 minutes is enough for them to transmit the information, the data they have, and also to get new instruction. Then they will dive again. So for I think like for example, like Australia, I know of Australia and the US, they also use the underwater glider as like a scout, a scout team in front of the submarines. That means the glider go first, the submarines at the back. This is for defense application, but it is water because the depth and allow the robot to glide enough depth to glide. Like our water, like the Malaysian, like South China Sea, like Java Sea or South China Sea is very shallow, 100 meter, not enough depth to glide.
I see. Yeah, but really during gliding, so it's totally autonomous, just literally.
Yes, it is literally. And what you have is that if you have the start point and end point here, so when it goes down, the water, inside current will push it sideways. So when it goes up, it is way out from the original path. So they will change the rudder so that it will dive and make a turn. And then so that's why you have underwater glider from real data is going to have like like turning from. Because the water environment are very dynamic. There's a lot of underwater currents. So while it is the water, it is what we call floating. It is following the water current. That's why, Prof, there are many cases where these glider are caught by fisherman net.
I just wonder how you guarantee that it survives because.
But Prof, in the commercial glider, they have a GPS locator. So what happened is that you have the host in your station. Let's say at the port you have the station. When it is there are cases in Australia where the glider, they found the glider move on land and go on the roads. So apparently somebody have take it from the ocean and put at the back of their pickup truck and try to steal it. But the owner went to the house and asked for the glider.
I understand. Yeah, very interesting. Yeah, I just wonder whether if it's lost, it's impossible to find. Yeah, if it's caught, it could be detected, but it could be possible that because of this autonomous motion, that if it's broken underwater, and then it's no means to know about that.
Yes,
that's what
of course.
I wondered.
So this is a challenge. So nowadays the newer underwater glider, they have added a propeller at the back. So that means there are certain higher level of control. The early generation of glider, it is totally it is floating. It is like you can't control it in the water. You can only control it at the surface, and even that you can only control very minimum. That means you can control the change the rudder just like that. So, but this has been used quite widely now, because you can use this in the water for 1 month, 2 months without any problem.
Oh, very long life. Okay, thank you very much.
You can buy one, Prof. It is $150,000 one.
Too expensive for me.
For one.
Thank you very much.
Thank you, Prof.
Thank you very much, Professor Takada, for having a question and discussion in this session. Maybe, is there any other question from the participant? Any more question from participant? Another question, I think. So, I think it's the end of the question and answer session, Prof. Rizal.
Thank you very much.
Yeah, thank you so much, Professor Rizal Arshad from USM.
Thank you.
From your sharing of knowledge to us is a new thing for me, especially.
Thank you again.
Yeah. So thank you so much for Professor Rizal Arshad that already shared with us and answer all of the questions from the participant from the second session of this keynote speech session. So now this is the end of the keynote speech session. And before we close this session, I just want to remind you that we will have a photo session together. And also after this, it will continue by the closing ceremony and the announcement of the best presenter for each track. So stay with us until the end. So once more, I would like to thanks a lot to all of the participants, and of course to the distinguished speaker for today's discussion, Professor Junichi Takada from Tokyo Institute of Technology, and also Professor Muhammad Rizal Arshad from University Sains Malaysia. Thank you so much, Professor. Hopefully we can meet for another session, hopefully in the normal situation. Okay, so thank you so much. This is the end of this keynote speech session. I'm Widya Moro. Thank you so much. So I will send back the time to the moderator, to the MC. Please, Ms. Bella.
Thank you, Mr. Widya Moro. And now we're going to take the first photo session. And please, for everyone in this room, to turn on the camera and give your best pose. Okay, please turn on your camera for everyone who joined this event. Okay, how many slides?
Who's counting? 1, 2, 3.
Okay. There are 2 slides. Okay. And I will count it 1 until 3 for each slide. Okay. For the first slide, please give your best smile. Okay. 1, 2, and 3. Okay. For the last slide. 1, 2, and 3. Okay. Thank you, everyone. Okay. Now we are going to the third agenda. The third agenda is the announcement of the best presentation from each tracks. Okay. Okay. For the best presentation from artificial intelligence tracks is Mr. Zainal Abidin with paper title Classification of Indonesian Traditional Snacks Based on Image Using Convolutional Neural Network or CNN algorithm. Okay, for Mr. Zainal, please raise your hand. Mr. Zainal.
Yes, it's me.
Okay, congratulations, Mr.
Thank you so much. Thank you so much.
Yes, sir. Okay. Okay, next. For the best presentation from electrical and power engineering track is Miss Eman Hanuti with paper title Renewable Energy Contribution to Reach and ZEB with the help of HOMER software, a case study. For Miss Eman, please raise your hand. Miss Eman, where is Miss Eman? Congratulations, Miss Eman. You still mute, Miss Eman. I'm sorry.
Thank you for this opportunity. I'm very glad to share with you this chance. I'm very glad for choosing me. Thank you.
You're welcome.
Thank you.
And next, the best presentation from telecommunications, computer network, and wireless communication track is Miss Ifah Zulaiha Saiful Bahri with paper title Shuttle Bus Service with ride-hailing application. Where is Miss Eva? Could you please, okay, raise your hand, please. Miss Eva Saiful. Where is Miss Eva? Please turn on your camera, Miss Eva. We still couldn't find you. Hello, Miss Eva. Congratulations. Okay, next. For the best presentation from electronics and robotics and mechatronics track is Miss Nurul MD Yunus with paper title Pre-Processing Noise Reduction for Assistive Listening System. Congratulations, Miss Nurul. Okay, next. For the best presentation from signal processing and computer vision track is Miss Theodora Valeri with paper title Modified 555 Timer IC using only 2 comparators. Congratulations, Miss Theodora. Can you spot it, Miss Theodora? Okay. Hi, Miss Theodora. Congratulations.
Thank you.
And the last, the best presentation from Information System and Embedded System track is Mr. Asep Najmur Rahman with paper title Design and Implementation of Low-Cost Air Quality Measurement Instrumentation using Internet of Things platform and cloud-based messaging service. Congratulations, Mr. Asep. Okay, congratulations for all best presentation at the first ICE3IS 2021. And now we're going to announce the best paper of the first ICE3IS 2021. The best paper of the first ICE 3I1 goes to Muhammad Solihul Hadi, Bima Satria Rizky Sugiono, Maulana As-Siddiqui, Muhammad Alfian Mizar, and Dia Lestari from Universitas Negeri Malang, Indonesia. Also, Muhammad Irfan from the University of Tokyo, Japan, with paper title Mamdani Fuzzy Logic-Based Smart Measuring Device as Quality Determination for Grain Post-Harvest Technology. Congratulations, and please give a very big applause. Okay, a bit difficult because we are in virtual meeting. Okay. Okay, for the next agenda is the closing remarks of the ICE3IS chairperson that will be delivered. I'm sorry. The fourth agenda is the closing remark of ICE3IS that will be delivered by the chairperson of ICE3IS, Dr. Yesi Yusman. The floor is yours.
Okay. Thank you, Miss Bella. Assalamualaikum warahmatullahi wabarakatuh. Yes, honorable distinguished speakers, on first day, October 50, 2021, Prof. Dr. Sukamta from Muhammadiyah, Universitas Muhammadiyah Yogyakarta, and also Prof. Dr. Wan Abdul Rahim, Wan Muhammad Isa from University Teknologi Mara, and the second day, 16 October 2021, Prof. Dr. Junichi Takada from Tokyo Institute of Technology, Japan, and also Prof. Insinyur Dr. Muhammad Rizal Arsyad from University Science Malaysia. Alhamdulillah, thanks to Allah, the International Conference on Electronic and Electrical Engineering and Intelligent System has been held smoothly and successfully. And ladies and gentlemen, representing the Dean of Faculty of Engineering and Head of Department of Electrical Engineering, Universitas Muhammadiyah Yogyakarta, and as a chairman of ICE3IS 2021, thank you to all participants and presenters who have participated in this activity, both plenary session and parallel session. We will hold ICE3IS every year. I really hope that all authors and presenters in this ICE3IS can join next year also, and in an attractive offer, we invite your institution to join us as a co-host of ICE3IS 2022 next year, inshallah. For the ICE3IS 2022, God willing, looking the situation of Indonesia also, and on also the situation of our the world is, if no pandemic, we will hold this event in two ways, namely with face-to-face meeting and in Yogyakarta, and also we will facilitate an online meeting for our authors from countries or continent far from Indonesia. I hope that all participants will be able to benefit from the knowledge or new knowledge and find a new new college, and can collaborate in research maybe in next time, and that is very useful for the future, right? Okay. Thank you all. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Yese Yusman, for the speech. Ladies and gentlemen, finally we arrive at the end of International Conference on Electrical and Electronic Engineering Intelligent System 2021. Thank you for all their participation in the session. Allow me to conclude this ceremony by reciting Hamdalah together. Alhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
See you at the second ICE3IS 2022. Bye.
Bye.
Thank you so much, Professor Takada.
Thank you
from
very
Thank you,
Tokyo,
Prof.
and also
you very
Professor
much.
Arshad, Rizal Arshad. Thank you. See you next time. See you.
See you next time, inshallah.
much. Ya.
Bye.
Thank you, Dr. Fu.
Dr. Fu,
Thank you
yeah.
very much. Thank you.
Nice to see you again.
Yeah,
Fu.
yeah. Good to see you again.
Thank you so much.
Thank you. Please take care. Congratulations for organizing this conference. Yeah, hope to see
Thank
you
you
again
for,
next year.
yeah.
Thank you.
Yeah, thank you so much, Dr. Fu.
Bye. Take care.
Okay, see you.
See you.
Thank you. See you.
Hello, Mr. Tony. Masuk apa suaranya?
Kemarin pesan dikit.
Rizky Chandra. Aku live ya.